Welcome back to the class on search in AI. Today we discuss a new problem domain or a new problem category which is a subproblem in the search in AI. This is called the constraint satisfaction problems, or in short form is also called CSP. We have discussed state description problems and state space problems earlier, where we discussed state transformation rules, configuration, and then we also discussed how we are going to search this state space using various algorithms. Among this category of problems, one important category is related to one aspect which we have discussed earlier. Is given a configuration, we wish to determine whether this is a valid configuration. And in order to do that, we may need to solve a set of constraints. And the solution to these constraints become a very important aspect, which, unlike in some of the other problems which we discussed, did not exist to this level of importance. While some problems are in both the categories, constraint satisfaction problems have acquired a new subgroup in the search for AI major group due to this importance of having to solve constraints and the various techniques that are made available to do the same. This is what we shall discuss in details today. I have listed about 7 examples. The first example is called the arithmetic puzzle. As you can see, we have written characters BOB multiplied by BOB finally gives MARLEY. Now, this is a cryptic method of trying to represent certain letters and characters. Now, B, O, M, E, Y, etc. each of them would essentially have an integer value in such a manner that these constraints are satisfied for this multiplication, and we are to decode this value of these characters. So here these constraints become very important. The second one, which is the famous non-attacking queens problem, where we are supposed to place queens in such a manner on a chessboard that none attack each other. For example, this queen, this is a solution, this queen actually covers all these positions, and therefore nobody is there in that position, so there is nobody which attacks this queen, nor does it attack anybody. Given a solution here, it is easy to check. However, finding such a solution may not be straightforward. We have already discussed the crossword puzzle problem, where given a set of words, for example, if we write a word, let us say ASTON, then this word must be starting with T. This part of the crossword must start with a T. So these are the constraints. The map coloring problem comes from a situation where we would like to color a map. Here it is a simple 2D map. Later on it may be a very complex configuration of a topological space, where we would like to color the elements of the map in such a way, the regions of the map in such a way, that they are demarcated by different colors. And we shall see how we do that. In an airline, whenever we go to the airport, we see many flights are leaving and entering. The departure section of these flights or the arrival section of these flights, especially the departure section, needs to have certain gates. And because flights come in and go, we need to assign gates efficiently so that we are able to use minimum number of gates to satisfy all the flights, and therefore two flights which are having an overlapping time in some sort cannot be sent from the same gate. So how do we solve this problem? Earlier we have discussed the timetable problem, which is again a very complex constraint satisfaction problem, and we shall discuss it again a little more. We have seen the knapsack problem, a maximization problem. We shall now see how do we map it into a constraint satisfaction problem. So how do we formulate a constraint satisfaction problem? We formulate a constraint satisfaction problem by 4 items. The first is the set of variables. We typically define a finite set of variables v1, v2 up to vn, which defines the state space. For each variable, we define a domain. For vi, there is a domain di, and each domain can contain a set of discrete values or maybe a continuous domain in a particular range. Given the variables and the domains, in a state space problem, we had the state transformation rules. Here, state transformation rules are not needed. All we have is a set of constraints that need to be satisfied. These constraints could be unary constraints, that means within a particular variable. These constraints could be binary constraints between two variables. These constraints may be hyper constraints between a subset of the variables. And all constraints have a yes/no answer. That means whether this constraint is satisfied or not satisfied. We do not have state transformation rules. It is these constraints, these variables, all together ensure that how the problem state transformations will be defined, and we shall see that later. In addition to the satisfaction constraints, we can also have optimization criteria. This is optional. In many problems there is no optimization criteria. In many problems there are. And these optimization criteria can be max or min time. A solution to the constraint satisfaction problem is to find a consistent assignment to the set of variables. That means for every variable, we must find some value of the domain, and we must assign the values in such a way that the constraints are all satisfied. And if there is an optimization criteria, the optimization criteria are met. So this is the basic formulation. Its difference with the state transformation formulation is that the state transformation rules are not explicitly defined. Based on this formulation, we will see how the state transformations can be created. Let us come back to our few examples we have seen here. So here we have got our characters B, O, M, E, Y, A, I, L, and R. Each of these is a variable. So these are my variables. In addition to these variables, what do I have? What is the domain? Domain of every variable is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the domains of every variable. What are the constraints? The first constraint is uniqueness, which means that every such variable gets a unique value. That means no value of different variables are the same. The other constraint are those which come from this multiplication operator. So we must have B plus B must be equal to 1. and there may be a carryover, and if there is a carryover, then that carryover will come here and it will be performed. Now for a simple assignment, we can see that b cannot be 0, because if b is 0, then b plus b is supposed to get b. So we can always see that by assigning b equal to 0, this constraint is not satisfied. And we can write down the set of constraints, and then we need to find a solution. For the n queens problem, our objective, every row is a variable. Every row is a variable. And the domain of every row, as you can see, are the columns A, B, and so on. H. This is the domain. So we have got 8 rows, 1 to 8. These are my variables. And for every row, I have a domain. And my constraints are defined by the non-attacking queen's position. In the map coloring problem, again, the variables, we can convert the map coloring problem to a graph by assigning one node to every region, and if 2 nodes are adjacent, then we draw an edge between them. So here, every region is a variable. Every region is a variable. And we can choose the number of colors. Maybe we can choose 1, 2, and 3. And we say we want to do it in 3 colors. And then this forms the domain. And our objective is to assign colors in such a way that those which are connected by an edge, nodes which are connected by an edge cannot get the same color. This is the standard graph coloring problem. We know that for a map we can be done by 4 colors, but there are certain maps which could possibly be done by fewer colors. And that is how we define the constraints. Here again, the optimization criteria could be to do it by minimum number of colors. Let us look at the crossword problem. Typically, in the crossword problem, hint is given instead of the words. But here, for our purposes, we will assume that the word list is given. So in this case, we have got 1 across, 2 down, 3 down, and 4 across. These are the 4 places we have to fill. So we have got these 4 variables. Variables here will be 1, 2, 3, and 4. These are my variables. So if these are my variables, then I get the domain. So the domain of every variable is the word list. Now, what are the constraints? I have a constraint between 1 and 2. I have a constraint between variables 1 and 2. I have a constraint between variables 1 and 3. And 1 and 2 means 2 and 1. 1 and 3 means 3 and 1. I have a constraint between variables 2 and 4. Similarly, 4 and 2. I also have a constraint between variables 3 and 4 and 4 and 3. Because 1 and 2 have a common intersection. 1 and 3 have a common intersection. 4 and 2 have a common intersection, and 4 and 3 have a common intersection. And we are supposed to choose exactly one word from this list for every slot. And in this case, we will assume that if one word is chosen for a particular slot, the same word cannot be chosen for the other slots. The gate scheduling problem. Suppose we know the departure time for every flight, that is given in this column. So there are 7 flights and the departure times are given. And let us assume that 45 minutes before the departure, the gate must be controlled. That means the gate must be assigned. And 15 minutes after the departure, the gate must be kept for this particular flight. So for us, our variables here would be these flight numbers F1, F2. So one variable corresponding to every flight. The domain of these flights are the gates, gate numbers. Suppose we have got 4 gates, then 1, G1, G2, G3 and G4 would be my. What are the constraints to be satisfied? The constraints to be satisfied are that flights having overlapping times cannot be assigned the same gate. For example, I can assign the same gate between F1 and F2 because there is no overlapping time. But if I look at F1 and F3, I will notice that F1 has the blocking period of 6:15 to 7:15 and F3 has a blocking period of 7 to 8, which means that their intervals overlap. Therefore, they cannot be assigned the same gate. The optimization criteria could be the number of gates. And a solution to that problem is obviously assignment of a gate to a particular variable. The knapsack problem, which we had seen as a state space problem earlier, where we had formulated it in terms of finding a subset of this set of elements. So the knapsack problem originally is defined as a set of variables, set of items S1, S2 up to Sn, each item having a weight, corresponding weight W1, W2 to Wn, and having a value V, V1, V2 up to Vn. The sac having a total capacity C, which is the capacity. We are to find a subset of the set S, which will be put into the sac so that the capacity of the sum of the weights of the subset chosen does not exceed C and the value of the elements chosen are maximized. We have already seen how we do this as a state space problem. We now see how we formulate it as a simple CSP. What we do here is that we choose the variables as S1, S2 up to Sn, and the domain of every variable is either it is not chosen or it is chosen. And if it is chosen, then the sum is, therefore the total sum, the value of the total sum is sigma. So if it is chosen, let us say, so if it is chosen or not chosen, we assign. So Si into Wi, the sum of I to 1 to n, this gives me my total, this one. And this total capacity must be less than equal to C. And what I really need to do is I need to maximize, this is my optimization criteria, this is my constraint satisfaction criteria, this is my domain, these are my variables, and my optimization criteria is I want to maximize the value of I equal to 1 to n Si into Vi. I want to maximize this value. and a solution is this assignment, which effectively means the ones which are 1 are the ones which are chosen and the ones which are 0 are not chosen. The timetable problem is probably one of the most complex CSP problems. Here we have got slots, that is, these are the time slots. Then we have got rooms where classes are held. We have got subjects, and subjects are taught by teachers and the students take the courses. So how do we assign what are our variables? What are our final variables? What are the domains of the variables? And what are the constraints to be satisfied? For example, we cannot have in the same classroom 2 subjects being taught by 2 different teachers. We cannot have a student doing the same class at the same time in doing 2 different classes at the same time, and the classes are held in 2 different rooms. Similarly, we have to write down all these constraints. Now, there is a very intricate optimization problem, because there is a physical movement involved, there is a total time involved. We would like to ensure other constraints. For example, if a class slot has got 3 lecture hours per week, we would like to typically break it down into 1, 1, 1 or 1, 2. That means 3 hours in 3 different days, or in 2 days, one is 1 hour, one is 2 hours. We would typically not like to have a theory class of 3 hours all in the same day, in different slots or maybe same slot or whatever. So these are some of the constraints that we need to satisfy. On the other hand, if it's a laboratory class of 3 hours, we would definitely like to have it contiguously at some point in time. So once we have these multi-layered constraints, the optimization problem relates to having as much of free slots for the student. We would like to fit everything in the total duration of the classes. We would like to minimize movement time. For example, distance between 2 classes is such that it takes 15 minutes to go from one class to another, and we definitely cannot have 2 consecutive classes that way. So that would be a constraint, and then we can put in movement time. Now when online classes are there, in the era of online classes, then there are some more additional constraints, because movement is not there. There are several issues that we need to relook when we have online classes. So I would recommend to students that you would please try to formulate the timetable CSP both for physical classes as well as for online classes. So now how do you solve a CSP? Having formulated a CSP problem, how do you solve a constraint satisfaction problem? In order to solve a constraint satisfaction problem, we apply 3 steps. The first step is what is called the creation of the CSP graph. The second step is, once you have created the graph, you apply a series of constraint propagation steps. And after having applied the constraint propagation steps, either a solution is found, or it is said to be not solvable, or the problem with reduced constraints still is not fully solved. Once it is not fully solved, we then have to resort to a search method. Then we have to start applying search methods. So let us try to understand each of these steps. To create a constraint CSP graph, we create a node for every variable. and assign all possible domain values to that variable. Then if there is constraints, then between nodes we draw edges. And if the edges are directional, then we draw directional edges. If the edges are bidirectional, we draw a normal undirected edge. If constraints are between a set of nodes, then we draw in that graph a hyperedge. What is a hyperedge? Suppose we have got these four nodes, then a binary edge is between this. A hyperedge of 3 nodes is drawn by just covering these 3 nodes by a set. So the first step we do is CSP graph creation. The next step is what is called constraint propagation. And in constraint propagation, there are 3 kinds of constraint propagation. One is called node consistency, where we check whether a node is consistent with respect to its domain values, and we remove those domain values which are not consistent with the node. The second is called arc consistency or edge consistency. In arc or edge consistency, we look at an edge, whether it's a normal binary edge or a hyperedge. For a binary edge, we look at the 2 nodes and we try to find out whether there are some values in any one of these 2 variables which are existing now, but possible values in their domains, which do not have a partner value in the other domains. By that we start removing this, and then we apply a path consistency or a K consistency, where instead of taking only one edge, we take a path of nodes and then try to see whether that path is consistent. And using this, we go on applying these consistency till nothing else can be done. In that case, sometimes it is found that by applying consistency there is no solution, then we can terminate. On the other hand, we can find a unique solution, and finally we could reduce it, but we may not be able to solve it. And once we have reached this position and have not solved the problem, then we start applying search. And from this type of problem definition, the state transformation rules are automatically defined by assignment of values to the variables, and by that new states are created, and we shall see that later on. And for such algorithms, depending on the type of the constraint graph that we get, the CSP graph, the algorithms may differ. There are various specific areas of trees, perfect graphs, interval graphs, where the problem has got a straightforward, easier solution. Otherwise, you have to apply backtracking. And there again, how will you backtrack, which variables will you do, all that, and what sort of look ahead you will assume, what sort of forward checking you will do, what sort of dynamic constraint propagation you will do, and what sort of dependency directed backtracking you will do are the issues involved. Finally, we will also see that we can convert this to a logic problem called the satisfiability. By converting it to a logical satisfiability problem, we can also solve CSPs using the solutions to logic problems. So this is the overview of CSP, and now we shall see how we do each of these steps one by one. Let us say how we will create the CSP graph for the crossword. We know that there are 4 variables, so we create 4 nodes. The domains for every node, we initially assign that we know that all the values in the word list are initial domains for every variable. So that means each of them has got a word list. The second thing that we have to do is define the constraints. We know 1 and 2 are constraints, so we draw an edge, and this is a two-way constraint, therefore it's an undirected edge. 1 and 3 have constraints, 2 and 4 have a constraint, and 3 and 4 have a constraint. This is how we draw the constraint graph. So this is the constraint CSP constraint graph for the crossword puzzle. For the airline problem, we know that we have got 7 variables. So we will have all these 7 variables: F1, F2, F3, F4, F5, F6, and F7. And the domains for each variable will be gates. Let us say we are going to assume, let us say we want to try to do it with 3 gates. Gate 1, Gate 1, Gate 2, and Gate 3. So the domain of every variable is Gate 1, Gate 2, Gate 3. And then how are the constraints? We check whether 2 variables overlap. F1 and F2. F1 and F2 do not overlap, so there is no edge between F1 and F2. F1 we check with F3, and we find that F1 and F3 overlap. So we draw an edge. Then we check F1 and F4. F1 and F4, this is F1, this is F4, they don't overlap. F1 and F5 don't overlap. F1 and F6 don't overlap. F1 and F7 don't overlap. So we have satisfied there is only one edge for F1. Now let us see F2. We don't need to check with F1 because we have checked F1, F2, so we don't need to check F2, F1. Now we see whether there is an overlap between F2 and F3. And we see that there is an overlap between F2 and F3. So there is an edge between F2 and F3. Then we check whether there is an overlap between F2 and F4. And we see that there is no overlap. Then again F2 and F5, and so on and so forth. By doing this sort of a thing, we get this constraint graph for airlines. For example, F1 and F3 are constrained, we had seen. F3 and F2 are constrained, we had seen. Now see F2 and F6. F2 and F6. There is an overlap. This is 745 to 845. This is 815 to 915. So F2 and F6. And F6 has got overlaps with F5, F4, and F4 has got overlap with F6. And this is how the constraint graph is drawn. And the domain of every one of them are these 3 gates, let us say 1, 2, 3, where we want to assign it to. We could also define this as a problem of optimization. So we would like to choose maybe 10 gates or 7 gates, because beyond 7 gates are not required because there are 7 variables. We could choose 7 gates and then try to find out the minimum number of gates. So the other option is we could choose 7 gate variables, gates as the domain. Domain could be 7 gates, but we would like to minimize the number of gates. After having assigned the CSP graph, the second step we had discussed was the constraint propagation step. And in the constraint propagation step, we will first check what are the constraints. So there are 3 types of constraints which we had seen. Node constraints, whether a value is valid for a particular node. Then there are edge constraints between 2 nodes, which is the typical CSP variation. And there are higher order constraints, which is between a subset of nodes, as we had seen in the knapsack problem. We had seen in the knapsack problem there is no edge constraint, but there is a subset constraint saying that a subset of chosen nodes must have a weight less than C. Now, how do we check consistency? So the first consistency is called node consistency. For every variable, we will remove all elements of the domain which were initially assigned that do not satisfy the unary constraints of the variable. And by this, we reduce the domains by removing all elements which are not consistent with the domain. For example, in the crossword puzzle, if there are 4 slots, then neither a 3 variable, nor a 5 variable, nor a 2 variable, only 4 variables are valid. 4 letter words are valid. So for that 4 slot variable, only 4 letter words will be valid. The next step is the edge consistency or the arc consistency. It is also called edge consistency. Now what we do here is that given 2 domains which have an edge, and let us say this is variable v1, this is variable v2, and let us say v11, v12, v13 are 3 variables here, and here let us say v21 and v22 are the 2 domain values. So we have got 2 variables with one edge, common edge, which is the constraint between them, and we have got 3 values of the domain in v1 and we have got 2 values of the domain in v2. Now what we do is we look at v11 and we check whether there is any consistent value here. If there is, we have nothing to do. But suppose v11 with respect to this constraint C between v1 and v2, none of them satisfy the constraint with v11. Then v11 can be removed. So this is how we say that for every element xij of di, for every edge, that means we do this for every other edge. If we cannot remove it here, we check it for other edges. So for every other edge, we check whether this has got at least one consistent value in every possible connected variable. And if it has got in every other connected variable, it remains. If it does not, even in one variable there is no value which is consistent with it, then we can remove it. So this is how we do this. And once we have removed one, then we iterate and try to find out and apply arc consistency till no further reduction happens. And at the end of it, or even in the middle of it, we could find some domain becoming empty. And if some domain becomes empty, then obviously there is failure. There is no solution. Otherwise, we could end up with one element in every domain, which is a solution, which is consistent. Or we could have some multiple values, after which we will actually have to apply a search as mentioned earlier. K consistency or path consistency, instead of one edge, looks at a path and tries to find out whether any value x11 has a consistent label in all of these paths. So it is almost like trying to find a solution. So larger path consistency is less used and arc consistency is more used. And as I said, after applying this, either we find a failure, or we find that there is a unique solution, or we find that we have to now apply search because there is no unique solution. There are possibilities which exist. Let us see how we do this for the crossword puzzle. For the crossword puzzle, this is my word list. And then after applying node consistency, I know that 5-letter words will apply for variable D1. So only 5-letter words are there. For D2, only 4-letter words are there. For D3, only 3-letter words are there. And for D4, only 4-letter words are there. Now this is how we have applied node consistency. Next, we will apply arc consistency or edge consistency. So let us see how we will apply arc consistency. We will look at D1. We know that D1 in our constraint graph, as we had seen earlier, we had D1, we had D2, we had D3, and we had D4, and our constraint graph was like this. So now we will check D1 with respect to D3 and D2. So let us check this value, A star, A star. If A star is to be there, then we know that something must start with T, because the third letter must be the first letter of D2. So there is something to start with T. So with respect to D2, A star is still consistent. Let us look at happy. There must be something starting with P, and we have two elements starting with P, so this is fine. Let us look at hello. So there must be something starting with L, so this is also fine. Let us look at hoses. So there must be something starting with S, and that is also here. So with D1, D2, we could not reduce anything. Now let us see between D1 and D3. Between D1 and D3, we check. Now again we come back to A star. And then because it is A star, then the last letter here, R, must have be the first letter here. And there is nobody starting with R. Therefore, by applying R consistency, we remove A star. Second, we look at happy. There must be something starting with Y in D3 and nothing starts with Y. So we remove happy. Then we look at hello, and we have something starting with O, therefore we cannot remove hello. Then we have hoses, and we need something starting with S, therefore there is nobody starting with S, so we remove hoses. Now we see that there is only one element hello here. We can now go back to D1 and check D1 with D2 again, because D1, D3 has yielded some new values for D1. So now once D1 has been reduced, we again go back to D2. And now we don't need to check A star, happy and hoses, and we know that if we go from D1 to D2, already the third letter must start with L. So that is fine. Next, we will now need to check D2 with D4, because D2's third letter and D4's second letter must match. So let us look at life. Having looked at life, the third letter is V, and the second letter must be V here in D4. There is nobody whose second letter is V. Therefore, life cannot exist. Similarly, load. There must be somebody who's in D4 whose second letter is A. And we see in save the second letter is A. So we cannot remove, because there is at least one. Similarly, in loom, the third letter here is the second letter in load. Similarly, in peel, the third letter here is the second letter in save. The other peel, the third letter E is the second letter in its peel here. And in save, the third letter V is nowhere we have the second letter, so save gets out from here. The third letter L is also not a second letter here, so again this gets removed. Now once this gets removed, we can now check between D3 and D4. Between D3 and D4, we know that the third letter of D3 and the fourth letter of D4 must match. So T must match with somebody, and there is nobody matching with T, so this gets removed. K must match with somebody at the last and matches with talk, so this remains. Old must match with somebody, and that is with load, so these two remain. So after applying D3, D4, we are left with this. We can again go back to D1, D2, and hello still has D1. The third letter must be the first letter. So D1, D2, hello remains. Again, we can check D2 and D4 to see whether there is any further reduction. But we can also apply D4 with the others because these are two-way constraints. So that we have checked and found, and let us now see whether D3 D4 or D4 D3 has got anything. So here we see that we have an element live here and its last letter is E, but there is nobody here whose last letter is E in D3. So this gets removed. Similarly, load and old are there, but loom has nothing here. So loom gets removed. Peel gets removed, this peel gets removed, and save gets removed. But talk remains because oak is there. So now D4 has been reduced to two elements. And if we now check D2 and D4, we will go on reducing this further. And you can go on doing this to see whether it will reduce to a single domain or whether it will reduce to null clause. And if we want to do a little more, let us see if we do D2, D4. Now, once we try and do D2, D4, we could also do D4, D2. So if we do D2, D4, what is D2, D4? The third letter must match with the second letter. So A must match with the second letter, it matches. O must match with the second letter, it matches. But P, this A matches here, but this E does not match with this letter, so this goes away. Now let us apply D4 with D2. That means O here must be the third letter somewhere which matches, and A here must be the third letter somewhere which matches. And we go on now applying. Now we can apply D2, we can apply D1 with D3. If we apply D1 with D3, we notice that the last letter of D1 must be the first letter of D3, which is still consistent. Now let us come with D1 and D2. In D1 and D2 we have just checked. So we have to now systematically go on doing this till either there is null or there is some element left or they all become unique. So what is this arc consistency algorithm? The arc consistency algorithm consists of two parts. One is the revise arc. The revise arc does exactly what we were trying to do. We try to check for each x in di, that means for each value in that domain, if no value of y in dj allows xy to satisfy, then we delete this value from di. And once we delete a particular value, we notice that this revised is true. So we delete a value and say revised is true. Then we create a queue like our open list queue, and we initially put in all edges. Then we remove one edge at a time. We remove an edge. We check whether revise yields any change. If revise yields a change, that means revise this is true. If it is not true, we do nothing. If we just have removed this element from the queue. If it is a change, then we check if the domain is empty. If the domain is empty, then we return false. Otherwise, for every neighbor, we put this in the queue because there is a change, its neighbors again need to be revised. And we go on doing this till the queue is not empty, and then we check whether we have either a consistent value or a set of consistent values, and we need to proceed further. In the gate scheduling problem, suppose we have got 3 gates. So their domain is 1, 2, 3. 1, 2, 3. 1, 2, 3. And if we apply this, 1, 2, 3, we will see that by applying any sort of constraints there is no deduction, because for 1 there is 2. Every edge we cannot use the same gate. So it's like a coloring problem. And if we apply 1, 2, 3, nothing will happen. On the other hand, if we use only 2, 1 and 2, or if we use only one gate, we will see that constraints are not satisfied. If we use 2 gates, by arc consistency, we will not find any problem. But if we use 2 gates and apply a larger set of path consistency like this, then we will find a problem. So at the end of the arc consistency, we will end up with a subset in every domain. After getting a subset in every domain, we then have to do a search. And this search is a simple backtracking search, and the state space is created in the following way. For what we do is, at every variable, we then select an unassigned variable. So we select, in the search proceeds by selection of a variable. So we select an unassigned variable, and for that unassigned variable, we select a value in the domain. And that is what we assign in this state of the state space transformation. And by assigning different values for the same variable, we generate different children. And once we have assigned a value, obviously we again reapply the arc and the path consistency mechanisms. Once we reapply the arc and the path consistency mechanisms, then we continue this way. And if there is no solution, obviously we backtrack from here. Otherwise, we again choose another variable and assign various values and create the next stage. This is how we proceed to solve the problem. Backtracking algorithm is the one which uses depth first search, or it will use a depth first branch and bound if it is. Otherwise, if it is an optimization problem, then again we can use best first search. But if it is not an optimization problem, there is no point in using best first search. All we do is apply a backtracking algorithm, because the depth of the tree is the number of variables, and therefore the depth of the tree is fixed for every path in this tree, because we are choosing one variable in every state, and the branching factor is related to the domains of these variables. So what do we do in this gate scheduling? Suppose we want to schedule it with 2 gates. So initially is 1, 2, then 1, 2, 1, 2, 1, 2, 1, 2, and if we apply only arc consistency, nothing will reduce. So we start with this start state, and here we choose, say, F1, and we assign F1 to either 1 or 2. So here we assign F1 equal to 1, and here we assign F1 equal to 2. Once we assign F1 equal to 1 and F1 equal to 2, we get 2 children. So if we assign F1 equal to 1, let us say here, then immediately this cannot be 1 anymore. So by applying, now we start applying the arc consistency. If this is assigned 1, then we see that 1 cannot be here. And because this is 2, this cannot be 2. And because this is 1, this cannot be 1. And because this is 2, this cannot be 2. And because this is 1, this cannot be 1. And now that these two are both 2, you reach a failure. And if you apply f1 equal to 1, you will fail here. Similarly, if you apply f1 equal to 2, just by one assignment and propagation by arc consistency, you will fail here. And you will show that with two variables, you cannot do it. On the other hand, if you apply three variables, then you can see that you will get a solution, and I leave that for you to do. So the steps are, as mentioned here, after applying initial arc consistency, and you have got a place, now you choose a variable. The state space is generated by choosing a variable, and branching is done by assigning values of the domains to that variable and creating children where that variable is assigned that value. Once you create the children, then you again apply arc consistency, node consistency, and path consistency on each of these. Node consistency need not be reapplied, but at least arc consistency is applied. And based on that, either the nodes will fail or the nodes will have reduced domains, and then you choose another variable. And the depth of this search is the number of variables that you have. The branching factor at every node is the number of values that can be assigned. The n queens problem, that is how you do. You initialize it with no queen assigned. Then you choose the first row, that is your first variable. So the variable chosen is row 1. And once this row 1 is chosen, they are placed on the 4 locations of row 1. Now once you place it on the 4 locations of row 1, it is consistent. Similarly, now you will choose row 2. And you will generate the children. Now you can see in row 1, you cannot put, if row 1 is fixed, then row 2 cannot have this one or this one. Row 2 can only have in the 3rd column and in the 4th column. And you get here, and if you have chosen this one, then you can see that you cannot choose a variable below this. Because if you apply any node consistency, none of these rows are applicable. Because this row is taken away by the first variable. These 3 rows are taken away by the second variable. So here, by applying arc consistency, you just terminate here. Whereas you can proceed with this one with one more child, but here again you will terminate. And you can do that and see by this tree, for simple 4 by 4, you will terminate intermediate here with the arc consistency, and you reach 2 solutions. And these are implemented by a DFS or a backtracking algorithm. Because there is no optimization here, and all you have to do is apply a DFS so that it requires minimum memory. The maximum depth of the search is the number of variables, which is 4 here. So how do we increase the search? How do we apply strategies? As we have seen, we initially apply constraint propagation, and then we choose a variable. So the choice of the variable is very important. Among the ways in which you want to choose a variable, typical ways in which we choose a variable is choosing the most constrained variable. That means the one which has minimum remaining values, so that the branching factor is less, and if we choose those values, we may easily get a solution, though there is no guarantee. Or sometimes we may choose the most constraining variable. That means if we choose that variable which reduces the domains of the other variables drastically. Second step is, having chosen the variable, now I have to choose the values. Because it is a depth first search, and we have seen depth first search is directional, the ordering of the values is important. So we would like to choose that which provides us with maximum flexibility. Then there is a method called forward checking, where we try to see whether we can assign some more values, which is like a constraint propagation, and checking with a little bit of look ahead to see whether we really are able to check, we will reach a solution beyond this. The last is Once we have found a place which is not true, which node in that list, which is the open list which we talked about, do we go back to? Do we apply simple backtracking like normal DFS, or do we again choose a particular node to backtrack to, in which so that is called dependency directed backtracking. We have also discussed that SAT formulations can be done in logic, and once we use SAT, then we shall see when we do logic how we formulate CSPs in SAT. In problems like gate scheduling, in problems like Knapsack, in problems like timetable, there is optimization, and therefore when we come to optimization, then there's a minimization or maximization, and therefore we apply our DFBB, which we have discussed, or A star or IDA star. Some of these algorithms are applied. And in SAT formulation, we apply the constraint programming methods or solvers. There are other aspects also. How do we learn while we are solving these problems? How do we store such previously memoized items are very important criteria. And in general, these CSP problems are hard problems. They do not have easy solutions, and therefore they typically end up with a backtracking or a branch and bound search as applicable. Forward checking. Let us see what forward checking means. Forward checking propagates the information of assigned to unassigned variables, which means that it is a form of constraint propagation. Let us look at this coloring problem. In this graph, we want to color it by 3 colors. So initially, all the domains are, the 3 colors are GB. Now suppose we have assigned A as red. Once we assign A as red, then immediately we know B can only be GB and D can only be GB. Once we have seen B and D can be GB, then we know, then we try to see which is the next one we will assign. And suppose we assign C as G. Once we assign C as G, since C is constrained with both B and D, then obviously if this is red and this is green, we notice that both the values of B and D, only the value of B and D can be blue. But they also have an edge. So constraint propagation will immediately detect that both are blue. So this sort of constraint propagation is the reason with which we can reduce and rapidly reduce the search. So this sort of forward checking is a good idea. There are special cases in tree structured CSPs, whereas the ordinary CSP, the constraint satisfaction problem itself, as we had seen, is of order n squared d cubed, where n is the number of nodes and d is the number of domains. This is just the arc consistency algorithm. But in the case of the tree structured problems, it is easy to see that in tree structured problems, we could solve the whole CSP in order n d squared time, whereas in general the CSP solution is an NP hard problem. In many cases, the CSP problem can also be converted to a graph coloring problem. And we know that for special graphs like the perfect graphs, chordal graphs, and interval graphs, and for us, a category of interval graphs is the flight gate scheduling problem. Because in the flight gate scheduling problem, we have intervals and we have edges between overlapping intervals. And we can map the flight gate scheduling problem because overlapping intervals have their constraints between them. So the flight gate scheduling problem is an interval graph coloring problem. And for interval graph coloring problems, they can be solved in polynomial time. So many of these special cases of constraint satisfaction problems can be solved in polynomial time. Finally, the constraint satisfaction problem can be solved by SAT, that means by logic. And in order to do that, what we do is, suppose this is the gate scheduling problem, and suppose there are 3 gates. Then what we do is, for every gate F1, we define 3 variables, F11, F12, and F13. For every variable F2, we define F21, F22, and F23, and assign these are Boolean variables. And then we say that any one of them has to be 1. That is, one constraint is F11 or F12 or F13 must be true. This is one clause we generate. Then another clause is F21 or F22 or F23 must be true. So this is the second clause. Then the third clause that we generate 7 clauses for each of them. Then when there is a constraint between them, then we ensure that in between these two, either, because there is a constraint, we know that it can be either both F11 and F21, both of them cannot be true simultaneously. That means both F11 and F21, both are assigned to the same gate, even though they have a constraint, is not possible. Similarly, F12 and F22 cannot simultaneously hold. Similarly, so this cannot hold and this cannot hold, and F13 and F23 simultaneously cannot hold. And we write this whole into a Boolean formula and try to find what is called a satisfying solution. And this satisfying solution will tell us which of these gate variables are true. And we could exactly, instead of writing an OR here, we could write an exclusive OR here, which would mean we would find exactly one gate. So we could, CSPs can be modeled by SAT problems, and we could ask how you can do any such SAT problem. SAT has got very efficient solvers, and we can solve them by these SAT solvers. And we can also model optimization cases. We can model them by SMT solvers, or we can model them by a 0-1 integer linearing problem, or we can model them by constraint programming. And we shall see later on what sort of constraint programming problems can be modeled. And there are very well known solvers for that which may be used. With this, we come to the end of the constraint satisfaction problem, where we discussed this class of search problems, where variables are defined, domains are defined, constraints are defined, and we do not need to define the state space because they are all defined by a finite set of variables. So we have variables, we have domains, we have constraints, and then we apply constraint satisfaction. We apply constraint propagation and consistency algorithms, and we also then open up the state space when required by assigning variables and values. And because this is there, we will apply, if there is no optimization, then we will apply intelligent depth first search algorithms with various kinds of variable and value ordering, dependency directed backtracking, and forward checking. And if it is an optimization problem, then we embed a branch and bound or a best first search or an iterative deepening search around it. This is an important class of problems, and this forms the last category of the search problems, where we discussed earlier the state space problems, we discussed ordinary graphs, AND/OR graphs, game trees, and now we have discussed the constraint satisfaction problems. Thank you.